Hello everyone. In this video, we're going to talk about how we can do calculus with parametric equations. And so the first thing about calculus with parametric equation is how do we do a derivative in terms of a parametric equation. So here's kind of going to be our setup. Our setup is just like from before. We're going to define x and y with the parametric equations f of t and g of t. And we're assuming that f and g are differentiable. Now, another thing that we're going to assume is that y is also a differentiable function with respect to x, and figure out how that's playing along. Now, here's what we're thinking of doing. I'm going to use chain rule to rewrite and to take the formula of dy dt. When you learned this back in Cal 1, one way that you remembered the chain rule was derivative of the outside function evaluated at the inside function multiplied by the derivative of the inside function. Now, because y can be represented as both a function with respect to the parameter t, and y is also represented as a function with respect to x, then chain rule is going to look like, yes, derivative of the outside evaluated at the inside multiplied by derivative of the inside. And now I claim that since we now have dy dx, I can now solve for this if I know that the derivative of x with respect to the t does not equal 0. And I get that by defining by dx dt, meaning I can define a normal derivative that we dealt with back in Cal 1 and rewrite it in terms of parametric equation as follows: dy of dt over dx dt. Another way to phrase that is, tablet moving around, there we go. Another way to phrase that is the derivative that we dealt with before in terms of a parametric equation is the derivative of y in terms of the parametric equation t, or the derivative of the parametric equation married with the variable y divided by the derivative of the parametric equation married with the variable x, or g prime of t over f prime of t. And that's how we're going to talk about a derivative for a parametric equation. And so with that, we can able to find the slope of a tangent line in terms of this, because our first interpretation of a derivative was the slope of a tangent line at a point. And we get to use that to help us out when we try to sketch a parametric curve. Now, we can also define the second derivative of a parametric equation, where what we do is wherever y appeared in the previous equation, we're going to replace it with dy dx. So in other words, our second derivative in terms of parametric equations is the derivative with respect to time of the first derivative that we got over dx dt, or another way to phrase it, the derivative with respect to time of the derivative of the function that is married with y over the derivative of the function that is married with x divided by dx over dt. And that's what we're going to do. Now let's go ahead and start working through some examples. So we have a curve defined by the two parametric equations, x equals t squared and y equals t cubed minus 3t, which means in this case my f of t, or the function married with x, is t squared, and g of t, or the function married with y, will be t cubed minus 3t. And so part A is asking us, we need to find two tangents at the point 3, 0 and find their equation. And so what does that mean? We need to show what part A is asking. We need to find two equations of a tangent line that passes through the point 3, 0. And so let's go through that. So here's the first thought that I have. Since I know that the y value is 0, I'm going to put in 0 for my value for y, and I'm going to check what happens and what value for t will give me the value of 0 for y. And because each of them have a common factor of t, I'm going to factor out the t, and now I have that t times t squared minus 3 equals 0. So what that means is, in order for this equation to work, t would have to equal 0, or t will have to equal plus or minus 3. For those three values of the parameter t, I'll get a y value for 0. But what I need to now check for is if I plug those three values in for t, in f of t, do I get the x value for 3? So let's check that out. If I plug in 0 into f of t, I'll get that my s value will be 0, but I want to pass through the point s value 3, y value 0, and 0 is definitely not equal to 3. And I'll go ahead and tell you that if t is equal to positive or negative square root of 3, then I don't care whether or not it's positive or negative. Because of the square, the negative sign will go away anyway, and the square root will cancel with the square, and I'll get an output for 3. And so that means I'm going to neglect t equals 0, and I'm going to look at t equals plus or minus 3. Now, why do I care about the value for t? The reason why I care about finding what values for t will give me the point 3, 0 is when we take the derivative and try to find an actual slope at the tangent line, these are going to be the values that we evaluate our derivative at. So we will evaluate the derivative at t equals plus or minus square root of 3 to obtain the slopes of the tangent lines. So that's what that work has told us. It tells us that the actual values that we're going to plug in are plus or minus square root of 3. So now let's go ahead and take our derivative. we're going to do dy dx. Using our formula for parametric equations, it's going to be the derivative of g of t over the derivative of f of t. G of t is t cubed minus 3t, so that will be, derivative will be 3t squared minus 3, and then the derivative of ft squared will be just 2t. And now, with that, I now have my general derivative. Let's plug in some points. I'm going to now plug in negative square root of 3. Let's see what I get. I get 3 times negative square root of 3 squared minus 3 over 2 over negative square root of 3. Negative square root of 3 squared will give me 9. 9 minus will give me 3. 3 times that 3 will give me 9. Minus 3 will give me 6. Divided by 2, negative square root of 3. And I have, after simplifying, I will have 3 over negative square root of 3, which simplifies down to negative square root of 3. So I now have one slope for one of the tangent lines. Now let's see what happens when I plug in positive square root of 3. Well, I'm going to go ahead and tell you it's not going to be really interesting because it's going to be repeating the same work. The only difference is I'll have a plus sign instead of a negative sign. Meaning, I'll have 3 square root of 3 squared minus 3 over 2 square root of 3. And I'll have 6 over 2 square root of 3, 3 over square root of 3. And then I'll just get square root of 3. Alright, so now I have the two slopes for my equations. Let's go ahead and write down the general equations for the tangent line. So I need to pass through the point 3, 0, and I now know the slopes for my two equations for the tangent line. Well, point slope form tells me that I will get yes, plus or minus 3 as minus 3, which means my two equations of the tangent line will be s equals positive square root of 3 times x minus 3, and y equals negative square root of 3 times x minus 3. Let's make that 3 a little bit prettier. There we go. And there are my two equations of a tangent line for that. All right. And now, let's go ahead and try to answer part B. Let's find the points on my parametric curve where the tangent line will be horizontal or where it will be vertical. Let's start off with horizontal. So just like before, in Cal 1, the derivative is interpreted as the derivative or the slope of my tangent line. That should be just 2t. And that means I need to have this guy equal to 0. Well, the only way that that's going to equal to 0 is if the numerator equals 0. So 3t squared minus 3 equals 0. Well, they have a common factor of 3. That's going to be 3t squared minus 1 equals 0, which will be t squared minus 1 equals 0. Then I solve for t squared equals 1, which means that t would equal positive and negative 1. And so I'm going to plug that in to my equations for x and y. And so let's list them out. the corresponding points, if I plug positive 1 in for x and y, plug 1 in, I will get 1. Plug 1 in, I will get negative 2. So one of my 2 points that will give me a horizontal tangent line is 1, negative 2. And then if I plug t in, t equals negative 1, into the equation corresponding to x and y, I'll get the point 1, 2. So those are my 2 points in which I will get a horizontal tangent line. My work for vertical is the same amount of work. Now, if I say that I have a vertical line, then that means the slope of that line is undefined, meaning I need to figure out what values for t makes this undefined. And a way to make that undefined very quickly is to make the denominator equal to 0. So that means if I want that, I need to set 2t equals 0, which means t will equal 0. And if I plug 0 into both the equations corresponding to x and y, I'll get the corresponding point of the origin. So that means at the point 1, negative 2, and at the point 1, 2, I should expect that the slope of my tangent line to be 0. And at the point 0, 0, I should expect to have a slope that is undefined for the tangent line. And now we're going to determine when I'm concave up or concave down. Well, we know how to do this from Cal 1. We look at the second derivative and we check where I am positive and where I am negative. And so let's figure that out. So that means we're going to take the second derivative of the equation we've been dealing with before, which means we're going to take the derivative with respect to time of what we have from the previous step, and then divide that again by dx dt, or f prime of t. So we're going to take the derivative of what we had before, which was 3t squared minus 3 over 2t. If I divide the derivative of the function that is married with that, so 2t. If I take the derivative of this guy, I'll have to do quotient rule. And I don't like quotient rule, and I try to avoid that with a passion. So to avoid me from using the quotient rule, I'm going to rewrite the expression in pink as 3 halves t minus 1 over t. To give you context as to how I got that, since I have a common factor of 3 in my numerator, I factored out of 3. I went ahead and put 3 halves up front to give me t squared minus 1 over t, which gives me the expression t minus 1 over t over 2t. Taking that derivative gives me 3 halves times 1 plus 1 over t squared over 2t. And after simplifying, what I'm going to get is 3t squared plus 1 over 4t cubed. The reason why I got that is when I move the 3 halves to the denominator, I'll get 3, 1 plus 1 over t squared over 2t. And then what I did was I factored out the 1 over t squared to transform it into t squared plus 1. And so let's think about what makes this positive and what makes that negative. Well, first of all, I can't have 0 for t, because if I plug 0 in for t, my second derivative will be undefined. But I can make this observation. No matter what values I plug in, for numerator, as long as it's not equal to 0, my numerator will always be positive. Always be positive for all t. And that's because of that square. In this case, I will include 0. Which means if I'm going to change from positive to negative, it's going to be dependent on that t cubed. And that t cubed will be greater than 0 if t is greater than 0, and it'll be negative or less than 0 if t is negative. So what that means is I will be concave up when t is positive, and I will be concave down when t is negative. And so with that information, let's try to sketch this curve. So first, let's plug in some points that we know. I know the points in which I should have a horizontal tangent line. So at 1, 2, and at 1, -2. Keep in mind that those are my points where I should have a horizontal tangent line. I also know that at the origin, I should have a vertical tangent line going through that. And I'll go ahead and put 3, 0 to note that I am going to be passing through that point eventually at when t is either positive or negative √3. Keep in mind that at 1, 2, I had that when t was equal to -1. Because I'm negative here, that means I'm going to be concave down. I'm going to keep following that as I keep going. And essentially I will form a little fish, knowing that I'm concave up when t is greater than 0. And I'll note that that's when I got when t equals 1. And so the parametric equation, the flow, looks like that. Alright, let's move on with another example. Let's try to find a tangent for this parametric equation. It's called a cycloid. You don't have to worry about that. The reason why it's called a cycloid is if you try to graph it, it looks like a cycle going through back and forth. But I say we can go ahead and start answering questions like find a tangent of the cycloid at the point where I equal 1/3. And so what does that translate to? It translates to take the derivative and then evaluate when I plug in pi/3 for my parameter. So using our formula to find the derivative, it's going to be the derivative married with y divided by the derivative married with x. Taking our derivative, now in this case r is just being treated as a constant, so I'm going to take derivative of 1 minus cosine of theta, which means I'll just have r times sine of theta, divided by, let's put a parenthesis over that theta. There we go. Divided by r, derivative of r times theta minus sine of theta, which will give me r over 1 minus cosine of theta. Now I see that I have an r on the numerator and denominator, so I get to cancel those out, leaving me with sine of theta over 1 minus cosine of theta. So there's my derivative, and now I'm going to plug in pi over 3 for theta. And what I get is, well, first off, let's go ahead and list out what I get for x and for y. If I plug that in for x, I'll get pi over 3 minus sine of pi over 3 equals to r pi over 3 over root 3 over 2. I'm not going to try to simplify that because that'll just be ugly. Y equals to r 1 minus cosine of pi over 3. And after simplifying, that should give me r 1 minus 1/2, which will be r over 2. And then my derivative will be sine of pi over 3, which will be root 3 over 2. 1 minus cosine of pi over 3, which will just be 1/2 at the end. Meaning I'll have the square root of 3. Meaning if I graph this, at the point where my s value is r times pi over 3 minus root 3 over 2, and my y value for that point is r over 2, then then the slope of the tangent line at that point will be square root of 3. Let's go ahead and start answering the question again about when am I horizontal and when am I vertical for this guy. Now, just like before, for horizontal, we need to find out what makes the derivative equal to 0. Well, that means the numerator have to equal 0. So sine of theta equals 0. Well, not only that, I do have to be a little bit careful, because keep in mind that I'm not giving any restrictions for x. So here's why I have to be a little bit more careful. So if I graphed my unit circle, we know that the values that will make sine 0 very quickly in terms of my unit circle are when my two y values are equal to 0. The caveat is, if I looked and picked that point mistakenly, then at my unit circle that's 1, 0, which means cosine at that point will be 1. But in my denominator, if I pick, say, 0, then I'll have cosine of 0 equals 1, and I'll make the denominator undefined. So for this case for horizontal, I now have to be more careful and also make sure that 1 minus cosine does not equal 0, or make sure that cosine of that angle does not equal 1. And what that means in my unit circle is I have to guarantee that I always land at that point to give me a horizontal tangent line. And the way that we can guarantee that is the following. We know back from when we learned trigonometry and when we learned pre-cal that we land by here at that point when my angle equals to a multiple of 2 pi, where n is an integer. So for example, if I plug in 1, I get 2 pi. If I plug in 2, I get 4 pi. And the reason why that's the case is because sine is periodic with a period of 2 pi. So to guarantee that I land at the point underlined in blue, I'm going to do 2n minus 1 pi, where n is an integer. And the reason why I'm choosing that point is because at 2n minus 1, that's essentially saying I tried to make a full rotation about the unit circle, but the minus 1 told me, nope, I did not. I only rotated here. And in anchoring at that point, I would do a full rotation back to that point. So what the 2n minus 1 does is it resets where I begin rotating. Not began, that's past tense. Begin rotating on the unit circle. And so I want to do that to make sure I'm guaranteed that. All right. And I'm going to give us more room to talk about how we get a vertical tangent line. So I say, like before, we get a vertical tangent line when the slope is undefined. So sine of theta over 1 minus cosine of theta, that means I want that guy to be undefined. Well, the way that I need that to be undefined is to be of 1 minus cosine of theta equals 0, or cosine of theta equals 1. Well, the way that I could get cosine of theta equals 1 is, as I mentioned for horizontal, in my unit circle, I need to land at the point 1, 0, which means that theta will be 2 pi n, where n is an integer. And that's our thought process with that. So here's what we're thinking for this example, is that I get a horizontal tangent line if my angle is a multiple of 180 degrees about the unit circle, and I get a vertical tangent line if I do a full rotation about the unit circle. And that's how we're going to tackle this type of problem. And that covers derivative for a parametric equation. But derivatives aren't all of calculus. We also talked about integrals. And so let's talk about how we do a definite integral in terms of a parametric equation. Here's our idea. If I can express y equals a function capital F of x, then we learned way back in the day that the definite integral is just the area underneath the curve from A to B. And so I say I can rewrite this formula as either by using my substitution rule for integrals. To let y'all know what I mean by substitution rule, I'm referring to U sub. And since it's been a while since we talked about U sub, I want to do a quick recap. And so the theorem that I'm referring to is we're doing a definite integral where I need to do a U sub. Again, I'm writing this form because I'm doing the general form for a U sub, for the integrand in the U sub. Then what we do is, if we let U be that function g of x, then what's happening is we plug in g evaluated at a into the as my lower bound, g, or the u, plugged in my upper bound, old upper bound, as my new upper bound. And then I rewrite this as f prime of u du. And in this case, what's going on is for my substitution, I want to let f be, or x be dt, f of t. Now let's see how this equation changes. By differentials, that implies that dx over dt equals f prime of t, which further implies if I multiply both sides by dt, I get dx equals f prime of t d of t. In this knowledge, I'm using differentials from way back in the day. And so let's talk about what my bounds are going to be for that. It's going to be based off of what bounds I have for the parameter. So in my original integral, my bounds a and b are values of x, meaning a and b are going to be my parametric equation x evaluated at one of those 2 points. Now I don't know which order it is. It could be my parametric equation with x evaluated at alpha, or my parametric equation for x evaluated at beta, and vice versa. And so because of that, I can have 2 possible scenarios for my definite integral. It can either be the integral from alpha to beta of g of t f prime of t d of t, or the integral from beta to alpha g of t f prime of t d of t. And that's kind of our idea from that. And that is a typo. That should be g, that should be f prime. So let's recap. The reason why the g of t is coming from is in terms of integrals, I'm assuming that I can express y as a function that we dealt with normally, which means I just have inputs of x. But I'm also assuming that I can write it out also in terms of parametric equations. meaning I can also set that equal to g of t. And using that fact that dx equals f prime t d of t, I substitute an in. Meaning my integral for parametric curves is going to be the integral from alpha to beta, either or. And the way we determine the order of alpha and beta is going to be determined by g of t, by the f of t. So let's go out here. Let's try to find the area under a cycloid where my parameter is between 0 to 2 pi. And so let's think about how we can do this equation for that, or integrate for this. So if I'm given the parametric equation originally, then what I'm going to do first is I need to figure out what A is and what B is originally. Well, because I know my bound for the parametric equation 0 to 2 pi, I'm going to plug in 0 and 2 pi in for my values for x. And the reason why I'm plugging that in for x and not y is because when I do my original integral, it's with respect to x, not with respect to y. So my bounds are going to be determined based on what x is. And if I do that, I'll get that my output is 0. And if I plug in 2 pi, I get 2 pi minus sine of 2 pi. Sine of 2 pi is 0, means I have 2 pi r, where r is just some number that represents the radius. And that will be my A and B. So let's try and integrate this guy. We have A equals 2. Now originally we have integral from A to B of the function with respect to y, of y with respect to x. So 2 pi r, 1 minus cosine of theta, dx, and I'm replacing yes because I know that equals y. Equals, based on my formula for integrals for a parametric equation, my bounds of the parameter 0 to 2 pi, r times 1 minus cosine of theta, times the derivative of the function with x. So r times, and let's go ahead and change that to blue, 1 minus cosine of theta d theta. And so I'm going to go ahead and multiply out the integrand. I'm going to get r squared multiplied by the integral from 0 to 2 pi. And if I FOIL out the 1 minus cosine, I'm going to get 1 minus 2 times cosine of theta plus cosine squared of theta d theta. Using the linearity of definite integrals, I can rewrite that as the integral of each term. So 1 d theta minus 2 integral from 0 to 2 pi of cosine of theta d theta plus the integral of 0 to 2 pi of cosine squared of theta d theta. And so I say 2 out of these 3 integrals are pretty easy to calculate. That one because it's integral of a constant. That one because it's just, we're going to take the integral of cosine, which we know the antiderivative is sine. This is something we haven't seen in a while. We have to do work to evaluate the cosine squared. And recall back from trig integrals. Remember when we talked about trig integrals, way back in Unit 2, that if we have a product of sine and cosine and both the powers are even, we're going to somehow rewrite it in terms of cosine of, or sine of 2 theta. And so let's go ahead and figure out how we can do that. So here's how we're going to do it. We know from our half angle identity that cosine squared of theta, we know that that equals 2. We know that equals to 1 plus cosine of 2 theta divided by 2. Meaning that I can rewrite the integral now as, back from our previous work, r squared divided by integral from 0 to 2 pi of 1 d theta minus 2 integral from 0 to 2 pi of cosine of theta d theta plus integral from 0 to 2 pi of 1 plus cosine of 2 pi, 2 theta over 2 d theta. Alright, and let's now go ahead and try to simplify that guy. So now we have r squared equal to the integral from 0 to 2 pi of 1 d theta minus 2 integral from 0 to 2 pi of cosine of theta d theta plus the integral from 0 to 2 pi. I'm now going to split this integral up. 1/2 d theta plus 1/2 times the integral from 0 to 2 pi of cosine of 2 theta d theta. And now all four of these integrals are going to be very quick to calculate. And with that, let's go ahead and do this. So if I do that, I get r squared equals 2, or r squared times antiderivative of 1 is just theta. Antiderivative of 2 times cosine of theta is 2 sine of theta. Antiderivative of 1/2 will be theta over 2. And then antiderivative of cosine of 2 theta will be sine of 2 theta divided by 2. And with that 1/2 up front, it will give me 1/4. All of that evaluated from 0 to 2 pi. I'll go ahead and tell you that at 0, well, that's 0, that's 0, that's 0, that's 0, so everything's going to die off. But at 2 pi, you get some stuff living. So let's see what's happening. I get 2 pi minus 2 sine of 2 pi plus 2 pi over 2 plus 1/4 sine 2 times 2 pi, so 4 pi. And then if I'm plugging everything in 0, I'll get 0. Well, sine of 2 pi, well, that equals 0. Sine has a period of 2 pi, which means sine of 4 pi is equivalent to sine of 2 pi, so that equals 0. Meaning it's going to be r squared times 2 pi plus pi or 3 pi. So I get that definite integral is 3 pi r squared. Whew, and that was a lot of work for one problem. But I say we're not done. We're talking about how we can use calculus on parametric equations, because we could talk about it again for arc length. So since it's been a very long time since we talked about arc length, here's the formula that we have back from section 6.5 of this course. I can rewrite this in terms of a parametric equation. Here's how. So first, I'm given a function of the form y equals f of x. Now I'm going to say that I could rewrite this curve in terms of parametric equations. And so here's going to be our idea for that. I already know what my derivative equation looks like in terms of parametric equations. And I now know from what we've done before what my integral looks like for parametric equations. So let's combine the two. I'm going to take the L equals my arc length, integral of 1 plus dy over dx squared dx. Using my integral, it's going to be from alpha to beta of 1 plus dy dx squared times f prime of t d of t. But I already know what dy dx is in terms of my parametric equations. That's going to be 1 plus the derivative that is with y, the derivative that is with x, all of that squared, times f prime of t d of t. Well, with that, here's my next note. F prime of t, I assume that that's positive. And because I'm going to assume that is positive, what I can do now is I can move that derivative inside the square root, giving me the integral of alpha beta of the square root of, because I moved the derivative of f of t inside the square root, then it's going to be f prime of t squared multiplied by 1 plus. And now what I'm going to do is I have a ratio, all being squared, so that's g prime of t squared over f prime of t squared d of t. And then if I distribute that f prime of t that's in pink, I will get the equation boxed below. And that is going to be our parametric equation formula for arc length. And so with that, let's correspond with some examples that we've done before. And so let's do example 2. So in example 2, we did a representation of the unit circle. Note that because I have sine x equals cosine of t and y equals sine of t, that corresponds to 1 rotation about the unit circle, since I restricted my parameter to 0 to 2 pi. So my arc length, and you can verify this using our formula from section 6.5, our arc length on the unit circle will be 2 pi. Well, let's see if we correspond with that. The derivative of the function with x, that is negative sine of t, and a derivative of the function that is married with y is cosine of t. And using our equation for arc length, that will be derivative of 0 to 2 pi of f prime of t squared plus g prime of t squared dt, which is integral from 0 to 2 pi of negative sine of t squared, but because that's all inside is squared, that transforms to sine squared of t plus cosine squared of t. Sine squared of t times plus cosine squared of t gives me 1. Square root of 1 is just 1, which equals 2 pi, which is what we were expecting. Now let's go back to our sample from sample 3, which is sort of like a sample 2. The only difference is I multiplied my angle by 2. And so we talked about in the last video that what that corresponds to for my parametric equation is I'd done 2 full rotations about the unit circle. Meaning, because I did 2 full rotations about the unit circle, and I know the arc length of going around once is 2 pi, what I should expect is that the arc length should be 4 pi. And again, you could verify that using our normal formula for arc length from section 6.5. In this case, dx dt will be 2 times cosine of 2t. dy dt will be negative 2 times sine of 2t. And let's calculate the arc length. Integral from 0 to 2 pi of the square root of 2 times cosine of 2t squared plus negative 2 times sine of 2t squared. All this side is square root. I can rewrite that as the integral from 0 to 2 pi of the square root of 4 times cosine of 2t squared plus sine of 2t squared. And just like before, cosine squared of an angle plus sine squared of the same angle gives me 1, which means I'll have left in the integral square root of 4. Square root of 4 just gives me 2. Meaning, after simplifying, I just get the integral from 0 to 2 pi of 2 times dt, or 4 pi, which is what we expected from before. And like I mentioned before, the latter is just twice the arc length of the unit circle because I'm traversing the circle twice. And so one thing that I want you all to note when you're doing the arc length for a curve is when you find a length from a parametric representation, make sure that your curve is traversed only once within the bounds I'm integrating over. And what I mean by that is, make sure that the curve that you're working with makes sense to what you're doing for the arc length. If I'm moving around that curve that I have more than once, I might miscalculate the arc length for that. And now let's go ahead and calculate the arc length for one arc of the cycloid, which again I'll let y'all remember that angle, or my parameter, is from 0 to 2 pi. So just like before, I'm going to calculate L equals 0 to 2 pi of the square root of f prime of theta squared plus g prime of theta squared d theta equals the integral from 0 to 2 pi of the derivative of the function with x, which is r squared, which is r squared times 1 minus cosine of theta squared plus r squared times sine squared of theta afterwards. Now let's try to expand that. Integral from 0 to 2 pi. Note that I have a common factor of r squared, and I'm inside a square root. So after factoring the r squared out inside that square root, and then taking the square root, I'll have an r. Now if I go ahead and multiply and span 1 minus cosine squared, I'll have 1 minus 2 cosine of theta plus cosine squared of theta plus a sine squared of theta d theta. I know from our trig stuff that this better equal 1. So I'll have r times the integral from 0 to 2 pi of 1 minus 2 times cosine of theta plus 1. So 2 multiplied by 1 minus cosine of theta d theta. And right now we're kind of in a pickle, because 1 minus cosine in the square root, don't know how to tackle that. Well, I say we can. And here's how we're going to tackle that. So let's recall the following. And it's going to be our identity for a half angle formula for sine, which is 1 minus cosine of 1 minus cosine of 2 theta over 2. Now, I don't have 1 minus cosine of 2 theta here. I have 1 minus cosine of theta. But I can manipulate that. Here's how I can manipulate that. If I multiply both sides by 2, and if my angle is not theta, but theta over 2, then if I plug in theta over 2, I'll just get theta. And have 1 minus the cosine of theta. And so here's going to be, alright, my first idea. Is first I want to make sure that the sine of theta over 2 is greater than 0. And the reason why I want to make sure of that is because I'm going to substitute in at 2 times sine squared of theta over 2 inside the square root. And when I take the square root, I'm essentially taking a radical outside of the square root. Meaning I'll technically have an absolute value of sine over 2. And I don't want to deal with that inside the integral. So I want to make sure that sine of theta over 2 is positive, so that when I take it out of the radical, I don't have an absolute value. But I can play around with this for a little bit. If I know that my parameter is between 0 and 2 pi, well then divided by 2 means that theta over 2 is between 0 and pi, or the top half of my unit circle. And the reason why I want to emphasize that is that guarantees that sine of theta over 2 is always non-negative. And the reason why that guarantees that is on my unit circle, sine corresponds to the y value of my unit circle, and 0 to pi is the top half, which means that all y values are positive. And so that guarantees that when I take the sine squared of theta over 2 outside of the radical, I don't have to worry about an absolute value. So this equals now 2 r times the integral from 0 to 2 pi of the square root of 2 times 2 times the sine squared theta over 2 d theta. Now what I'm going to do is, well, 2 times 2 is 4, and the square root of 4 is just 2. So I'll have integral from 0 to 2 theta of 2 after evaluating the square root. And because I now verify that sine of theta over 2 will not, well, there will be no way that will be negative, I'll have theta over 2. And I say now we get to profit. Because now that equals 2, 2r, 2 is coming from taking it outside of the integral of negative 2 times cosine of theta over 2, value from 0 to 2 pi. Plug in 0, I'll get cosine of 0, which is 1. Plug in 2 pi, I'll have cosine of pi, which is also a negative 1. And then using fundamental theorem of calculus, I'll have 2r, 2 plus 2, which means my arc length will be 8 times r. And now the last thing we get to talk about is surface area. And using all the techniques that we talked about so far, here's our surface area equations in terms of rotating it about the x-axis and rotating it about the y-axis. And so we're going to finish this guy off by finding the surface area of a sphere is 4 pi r squared. And we're going to use the fact that I can rotate about a semicircle about the x-axis. So, because I'm rotating about the x-axis, I'm going to use the first equation, which gives me x equals the integral from 0 to pi, 2 times pi times the equation that is with the variable y, so r times sine of t, times the square root of the derivative with the variable x. Derivative of cosine is negative sine, so minus r sine of t squared plus the derivative that is with the variable y, so r times cosine of t squared times dt, times the integral from 0 to pi of 2 pi r times sine of t times r squared, and I'm going to get that for both terms. So sine squared of t plus cosine squared of t after I factor out the r squared. I know that this gives me 1, meaning I should have the integral from 0 to pi of 2 pi r times the square root of r squared. And because the radius is positive, because I'm not measuring -3 inches. Oh, and I forgot the sine of t. My bad. Should be a sine of t times the square root of r squared dt. Simplify that. I'll have the integral from 0 to pi of 2 pi r times sine of t times r dt. Everything underlined in pink is a constant with respect to time. So 2 pi r squared times the integral from 0 to pi of sine of t d of t. Now integrating that, I get 2 pi r squared negative cosine t, evaluated from 0 to pi. And in doing that evaluation, I get 2 pi r squared, 1 plus 1, which equals 2, 4 pi r squared, which is equivalent to the surface area equation for a sphere. Alright, and that concludes our video for session 12.1. Hope you all have a great day, and make sure that you like, comment, and subscribe. Well, not comment, because I disabled comments.